The first important bit of circuitry we're going to be looking at is the program counter. So the inputs to the program counter is solely the clock, and the outputs are going to be, it's a 3-bit output that is supposed to count from 0 to 7 and then wrap back around. And so how that works is this is a finite state machine. So we have we store our present state in flip-flops. And then we're going to have some output logic that is based on the present state. And then we're going to go to the next state conditionally on the present state. So this is a Moore machine instead of a Mealy machine, because a Mealy machine would depend also on the inputs for which state we go to next. And so on each input, the flip-flop here will grab the value at D, and on the positive edge of the clock, it will output that to Q. And so the way that works is it relies on the fact that we use a slow inverter. And so clock and not clock can both be positive at the same time. So it'll look a little bit like this. So clock and then not clock is still high, and then it drops down. And so because there's this overlap here, it allows for us to grab the positive edge of the clock and update Q based on that. And so each time Q gets updated, it'll follow this path down here, and it will go through the next state logic. For instance, for bit 0, it is just going to be inverted each time. And then for bit 1 and bit 2, the logic is a bit more complicated, but it just allows us to count up to the next state. And so after all the logic is propagated through, here, 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 we now have new values on D. And so when there are new values on D, on the positive clock edge, they will then be set onto Q, and then the whole cycle continues again, allowing us to count up. And in the actual circuit, we can see its kind of place. Here we have the clock going in, which allows us to parse or allows us to count up on each positive edge. And then we are outputting the clock into a couple of current boosters, current boosting buffers. And that's going into a decoder, which eventually allows us to choose the instruction. So that's all the program counter is. It's just counting up and telling us which instruction we are currently at. And yeah, some important metrics for the block are you want to keep in mind what the fastest path is, or what the slowest path is, sorry. Because the slowest path will tell you how fast you can operate your clock. And for instance, we also need to have a fastest path sometimes, not always, because here, if in the D flip-flop you have too long of an overlap between your clock and not clock, this inverter will actually update too fast the result, and it'll allow D to pass through again and could mess up your logic. And the way you simulate the program counter is you're just gonna have a clock pass in, and then you're just gonna watch the outputs and make sure that the outputs count from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7, and then back down to 0.